Hello. In the previous video, we have sketched the ST, VT and AT graphs for the vertical throw, assuming that the effect of air resistance is negligible. In this video, we are going to resketch the three graphs, but this time round taking into account the effect of air resistance. I'll strongly encourage you to take out a piece of paper and try to sketch your graphs yourself. So pause the video now and join me again when you are ready. Okay, I'll start with the VT graph because it's the most interesting graph. This black line here is the VT graph if there were no air resistance. It's a straight line graph because acceleration is constant, because the only force acting on the ball is mg, which is a constant force. With air resistance, it's not going to be a straight line graph because acceleration is not going to be constant, because the drag force caused by air resistance is not a constant force. In fact, its direction and magnitude is going to change continuously throughout the vertical throw. Let's start from the instance when the ball just left the hand. This is the instant when the ball is traveling upward at its maximum velocity. Since the ball is traveling upward, the drag force caused by air resistance is going to act downward. Notice that the drag force and the weight are both acting in the same direction downward. This is going to result in a net force that's larger than mg, which is going to result in an acceleration that's larger than g. This tells us that at the beginning, our VT graph is going to start with a gradient that's steeper than g, which is steeper than the original line. Now, as the ball travels upward, it's going to lose speed, and therefore the drag force is going to become smaller and smaller, and the net force is going to approach mg. Does it ever become mg? Yep, it happens when the ball is right at the peak. Right at the peak, the ball is instantaneously at rest. Since it's at rest, it's not pushing against air, so the drag force is 0. So the only force acting on the ball is mg, and so the acceleration is exactly g. So this tells us that when our VT graph touches the x-axis, that's the point when v is 0, it's going to have a gradient that's exactly g. So it's going to have a gradient as steep as the original line. After this point, the ball is going to accelerate downward. Since the ball is moving downward, the drag force caused by air resistance is going to be upward. Notice now the drag force is in opposite direction to the gravitational pull. This will result in a net force that is less than mg, and so this will result in an acceleration that's less than g. What this tells us is, on the way down, our VT graph is going to have a gradient that is less steep than the original line, since the acceleration is less than g. With these important landmarks, you should be able to figure out that the VT graph looks something like this. So it's a curve that becomes flatter and flatter, but has the same gradient as the original line when it's at the peak. Now let's talk about the area under the VT graph. The area under VT graph, of course, represents displacement. So this area here, this positive area, will represent the distance traveled by the ball on the way up. The negative area should represent the distance traveled by the ball on the way down. Logically, these two areas should be the same, since it's the same distance up and down. With this in mind, we should be able to figure out the time instant when the ball returns to our hand. Let's make some adjustment here. So, by my estimation, this looks like the time instant when the ball returns to my hand, because this area here matches this area here. And now we are able to make this interesting conclusion. Remember, when there were no air resistance, it takes as long for the ball to travel up as it takes to travel down. That was when the VT graph was a straight line graph. But now that the VT graph is a curve, and this sort of curve, we are able to conclude that it actually takes the ball a shorter time to go up than to come down. Okay, now that we have the VT graph, let's figure out our AT graph and ST graph. The gradient of the VT graph is of course acceleration. So just by looking that the gradient of our VT graph starts off being very negative but become less and less negative, we are able to figure out that the acceleration time graph should have this shape. Of course, there's an important landmark here. When the ball is at the peak, at the maximum height, the acceleration is exactly g. The physics also makes sense because, as we discussed earlier, when the ball was on the way up, both the gravitational pull and the drag force work together to decelerate the ball. So the ball decelerates at a rate faster than g when it's on the way up. On the way down, the gravitational force is trying to accelerate the ball downward, but the drag force is holding it back. That's why on the way up, the acceleration is actually less than g. Now let's look at the ST graph. The ST graph will look something like this. Again, the gradient of the ST graph is the velocity. So at the maximum height, you should draw the graph such that it has a zero gradient right at the top here. It should match this point here. And on the way down, at the instant when it reaches the hand, this gradient here should be less steep than this gradient here. This is because we know that the ball returns to our hand at a speed lower than the speed at which it left our hand. The shape of this graph should again convince you that it takes the ball shorter time to go up than to come down. Okay, so we are done with the 3 graphs. I hope you found them interesting. Ta-ta!